And now to cover the last big aspects in Chapter 9. Chapter 9 introduces this concept of the limiting reactant concept. So when we're talking about Chapter 9, we're looking at chemical equations. Well, chemical equations will naturally, as we go through those calculations, lead to this limiting reactant concept. So let's take a step back because we're tired of bicycles. Let's look at making some sandwiches. So to make a grilled cheese sandwich, we need 1 slice cheese and 2 slices of bread. Keep it simple. So if we were to now go through and look at all the different options we said had in our refrigerator that allowed us to go through and make this, we find that we have 5 slices of cheese and 8 slices of bread. Well, how many sandwiches could we theoretically go through and make? Okay. By this point, you should already be saying, okay, we're going to go through and actually set up the work for this. So sandwich, I'm going to go through and abbreviate as SW. I want SWs, I want sandwiches, and it's going to come from cheese. According to my chemical equation, it's where I'm going to have to start this process. 1 sandwich comes from 1 slice of cheese. How many slices of cheese do I have? I was given 5 slices of cheese, which means if I look at just the cheese, I could make 5 sandwiches. If we switch this up and now said how many sandwiches could I make given slices of bread, we'll again go through and make some abbreviations behind this. From our balanced chemical equation, 1 sandwich is 2 slices of bread. From our given information, we know 8 slices of bread. And if we set up our calculation correctly, we now go through and come to the answer of 4 sandwiches. So what we would acknowledge within this is that we can make it max 4 sandwiches. We can't make more than that. So one of the kind of mistakes that students will make as soon as we turn it into chemistry is they'll now say, well, now I can make 9 sandwiches. We ran out of bread, okay, at 4. So we can't make 9 sandwiches. It's not the addition of both of these. It's whichever one is the smallest amount, because that now limits the amount of things I can produce. So with the calculations that we've got here, we can go through and say, or conclusions that we can make from this process, is that number 1, we can make 4 sandwiches. Okay? And that tends to be one of the biggest questions that comes out of limiting reactant things, is how many sandwiches can you actually make? How much product can you make? Other questions that come out of this is what is the limiting reactant? Okay, so what allowed you to only make 4 sandwiches? Which material prevented you from making more? And in that case, that's going to be our bread. Our bread was the limiting reactant. It prevented me from making more sandwiches. Okay. Another question that could possibly come out of this, okay, would be referencing our cheese. Okay, well, the cheese didn't limit the reactant. Okay, so it's not a limiting reactant. We could reference it as a reactant in excess because we have a whole bunch of it. Okay, so those are kind of the limits of the questions that you can expect to see in 130. But if you moved into, say, 151, we could make these a little bit more challenging. And because all of our exams are going online, we might have to actually do that to really prove an understanding of the knowledge instead of you potentially kind of, unfortunately, I hate to say it, cheating with this. And so how could we take this a step further? Well, at the end of the reaction, what is left over? So at end, what do we have? Okay, so what you should be able to answer pretty quickly about what we have is, well, we have 4 sandwiches. Okay, we converted that across to products. Okay, so 4 sandwiches. We have no bread. Okay, there's 0 bread left over because we used it all. Well, how much cheese is left over? Okay, well, you might be able to do that calculation pretty quickly in your head. Okay, but to answer that question about how much cheese is left over, we're technically going to have to run a calculation. Okay, in that calculation, what we want to do is take our 4 sandwiches and say how much cheese did I need to make those 4 sandwiches. So we're running a new calculation. Okay, so this would only be done for the reagent in excess. Okay, so our reagent in excess in this case was our cheese. Okay, and I'm trying to come from 4 sandwiches. So what is the conversion between sandwich and cheese? In this case, 1 sandwich is 1 cheese. And I needed 4 cheeses to make those 4 sandwiches. Well, how much did I start with? I started with 5 cheeses, so I can now run my calculation that I have 1 cheese left over. Okay? Hopefully that makes sense. In this limited situation, okay, it was pretty straightforward. Those numbers were simple to work with. But what happens when we scale up into chemistry? The numbers stop becoming nice, easy 1 through 10 numbers. They're objects that we have no tactile response to. So we have to be able to effectively envision or pretend that what we're looking at is these larger macro scale objects to be able to come up with these interpretations. Okay, so again, this question of at the end, what do we have, is a much more advanced question. And I'm not going to lie, I honestly don't know if I would write that into a test question right now or not. Okay, because of our current system, I might end up having to write a question that involves looking at the excess at the end of a reaction. Okay, but this puts all of those pieces in relatively simple statements. Okay, we've got our conclusions that are now all drawn out. We've got the work. Of course, I unfortunately had to erase some of that work, but then we've got all of that work that was shown kind of up here. Okay, so other questions that could come out of this, okay, or statements. We have enough bread for 4 sandwiches, but enough cheese for 5 sandwiches. So how do we come up with that balance? We go with the smallest amount because we run out of bread before we can make all of our sandwiches. So the same thing is going to apply to our chemical equations. So let's again look at it at a simple scale first. Okay, and in the case of the bread, we're looking at a single unit. Okay, we're looking at those individual pieces. Well, in chemistry, our individual piece, if you will, we're going to use moles, okay? Because moles is an easier system to go through and use for all of those reasons that we addressed in past videos. Okay, so if we're going to go through and look at this question, what are we being asked to go through and do? Okay, well, I want to know how many moles of sodium carbonate are produced. This is effectively saying our sandwich. How many sandwiches can I make at the end of this? What are my given conditions? Well, first off, I'm given a balanced chemical equation, just like we were with the sandwiches, okay, on how to make that grilled cheese sandwich. And then I'm also given that I have 2 moles of sodium carbonate. I'm given that I have 2 moles of water. And I'm given that I have 1 mole of carbon dioxide. So one of the simplifications we might try and pull right out of the gate would be to write these as formulas to help us see these a little bit better so that we've got simple formulas to deal with. And then can I sort of erase that one, our CO2, and then our moles of, what was it, sodium hydrogen carbonate? Sodium hydrogen carbonate. Okay. This problem becomes slightly more difficult than our bread example or than our sandwich example because we have 3 reactants. We've effectively added mustard to our grilled cheese sandwich. And for those of you wondering about mustard, if you aren't putting mustard on your grilled cheese sandwich, you are a heathen. There, I said it. All right, so we've got the basic pieces outlined here. Okay, now what I would like you to do, just like we've done in the past videos, is take a second, hit pause, and try and set up some work behind this. And I'm being a little bit less snarky because this is the very first video of the day, so I'm feeling a little bit more smooth. So let's go through and establish this. Okay, as we did with the sandwiches, we're going to need to solve for each of these individual pieces. So I'm going to have to do 3 solves because there are 3 ingredients. And I don't know why I'm writing sandwiches. we should be writing sodium hydrogen carbonate, because that's what we're being asked to solve for in each of these cases. I'm going to have to delete that page reference, but I'll move it up to the upper right hand corner. This page reference is 59, or slide reference, if you're using the shared notes. Sodium hydrogen carbonate. Okay, so which reagent am I going to start with? Well, it doesn't really matter. Okay, I personally would reference, because I know I'm going into moles of sodium hydrogen carbonate, I personally would be pulling from the chemical equation, because the chemical equation guarantees that I've got a reference to moles of sodium hydrogen carbonate. And of course, we've got this long silence as I try and frantically write these things back in. Our moles of sodium hydrogen carbonate. And now I've got 3 of them, so I can decide where I want to go from here. Okay, so I'm going to go ahead and start with the very first thing listed up here, our moles of sodium carbonate. So where do I find the relationship? I got to be careful with my color coding here. I want the relationship between the moles of sodium carbonate and the moles of sodium hydrogen carbonate. Again, we aren't switching to colors here. This has to be given information. That relationship between these two things has to exist. Okay, and it does exist in the chemical equation. So I would pull the coefficients from my chemical equation. There's 2 moles of sodium hydrogen carbonate and 1 mole of sodium carbonate. If we set up our expression, okay, that means we need to get rid of the moles of sodium carbonate. Am I given just the moles of sodium carbonate? That was that green thing that I started earlier. So 2 moles, we go through the moles of sodium carbonate, cancel, and we'd be left with the moles of sodium hydrogen carbonate, which in this case, I will color code out as a 2, which would be, color code is green. 2 times 2 is 4. Okay, so we've got 2 more solves. I'm going to suggest that you go through and pause and you try and set up the work for those 2 other colors. So we're looking at blue and black. So our H2O and our CO2. So pause, space bar, or just click the little random picture. And so hopefully your work looks very similar to this. And so when we go through and evaluate this, we would again pick the smaller number of all of our calculations, which means our answer comes out to be 2 moles of sodium hydrogen carbonate. So the most that I could possibly make would be 2 moles of sodium hydrogen carbonate. Okay, because we I started those conclusions of our possibilities, let's go through and look at all the possible kind of answers that we could look at. So one answer would be 2 moles of sodium hydrogen carbonate produced. Okay, that would be a valid answer, okay, to this particular question. What other questions could be asked? What was the limiting reagent? So CO2 is now a limiting reagent. We're also going to encounter the potential question of the reagents in excess. This one gets a little bit harder because there's 2 reagents in excess. I have sodium carbonate and H2O as reagents in excess. Okay, what do I have at the end of the reaction? Well, I'm going to have the 2 moles of sodium hydrogen carbonate. Okay, and then I'm not showing the work here, but what we would also have, where are we? Oh, dang, I may have to show work. Can I do that in my head? I can do that in my head. And 1 mole of the sodium carbonate and 1 mole of the CO2, because those were our reagents in excess, and we're only consuming 1 of those in the process of this reaction. Okay, so those get to be our big overarching conclusions. Okay, so hopefully that makes sense. So what I'm going to do is now erase the conclusions, because I want to be able to point at something that sometimes students key in on and jump on as a potential shortcut to this whole process. Okay, so if we erase all that, we'll notice that if we look at our answer, we said that this one, that black box, was the one that dictated pretty much where everything followed. Okay, and where a pioneering student might go through and do is say, well, if we look at the numbers associated at the very beginning, it's 2, 2 versus 1. Okay, well, 1 is a smaller number, so therefore CO2 must be the limiting reagent. It doesn't work that way. Okay, and I know in this case it showed that. Okay, and you don't have to take my word for it, because we're going to look at an example where it's actually going to change on you. Okay. And I could even make a secondary example. In fact, I think I might do that. This kind of comparison that you're making assumes that you're starting with moles. Okay? What if you started with grams? You can't pick just the smallest number just based off of that mass, because remember, the mass to amount of particles present could be really different depending on the molar mass. So you really have to go through a calculation process. Otherwise, all you're doing is guessing. And if you guess right, if it's multiple choice, you don't have to show your work. Great. Fantastic. You now have the answer. But you're now at a 50% chance of getting it right. Okay? And I don't like those odds. I don't want that for you. So I want you to go through and show the work, because that work is going to help you get the answer correct a larger than half the time percentage. Okay, and just to prove my point, we'll go through and do another problem here. So we've got this equation, which should look similar to you from the past. I'm going to give you a little bit of time here to work on this on your own. So again, I want you to pause it. I'll actually walk through this in here in just a second. But please actually go ahead and hit pause and attempt this on your own. Okay, so if we go through and now focus on this, how much water can we make? So right away we have a bad question, okay? Because how much in what units? Grams, moles, kilograms, liters? What's the unit that we're being asked for? Okay, so that was a poor job on my part, so let's go ahead and fix that. We want the much to be in moles. Okay, and if you ever encounter an instructor that gave you ambiguous results or an ambiguous question, call them out for it. Okay, and then you can tell them that I told you to do so, and they can come yell at me, and then I'll tell them they need to write a better question. So moles of water, it's what we're aiming for. What were we given? We're given moles of oxygen and moles of hydrogen. Okay, so the first thing we're going to go through and do is based off of what we said on the last slide. Okay, you go, oh, well, moles of oxygen is the lowest number. That must therefore be the correct answer. So we'll set up the work, because while we're going to pay attention to Mike in some places, we won't pay attention to Mike in other places. And we'll just go ahead and set up the work and walk through this. So I want moles of water, so moles H2O. I want a conversion factor that allows me to see the moles of H2O. So the moles of H2O comes from the conversion of a chemical equation. I'm just saying it's moles of oxygen, and so therefore, because it's 1, that makes it easier. I'll pull numbers from my chemical equation. For those of you secretly screaming, hold on to that scream for a second. We'll address that. Moles of oxygen, 1, and we'd say, well, we get 1 mole of oxygen. Ha! Mike, you must be wrong. And then you might be like, well, because Mike is such a genuinely nice guy, I'll trust him. I'll go through and show him that he is indeed wrong, and that my method, and by I mean a hypothetical student, that their method is better than my method. And we go through and we set up our work and we go, well, ta-da, 1.5 moles of hydrogen, 1 and 1. And look, when we go through and do this, we get, if I actually pay attention to my numbers, I get 1 mole of water and from the oxygen, and I got 1.5 moles of water from the hydrogen. You'd be like, ha, Mike, this method of just looking at this initial number worked, and you are wrong, Mike. And I'd be like, that's a valid point. It does appear to have worked in this case. But then I'm actually going to follow it up with a different question. And the question I'm going to follow it up with is, where did you get the conversion factor in purple? Okay? So that conversion factor in purple came from the chemical equation that was written above. Okay? And we've been writing this out before, right? Okay? We wrote out for those purple conversions, we would always write the BCE for our chemical equation. What's B? B is balanced. A balanced chemical equation. Is that chemical equation balanced? Well, sure enough, no, it's not. We would actually need to balance that by putting a 2 here, a 2 here, and a 1 here. Which means the numbers that you wrote into your purple conversion were incorrect. So you best check your work there and go ahead and fix that. So in the top one, it turns out that that is 2 moles of H2O to 1 mole of oxygen. And in the bottom one, it is 2 moles of H2O to 2 moles of hydrogen. So in the bottom one, your number is still 1.5. So dang, I must be wrong still. Okay, so we're still going to come out with the oxygen being the limiting reagent. Except 1 times 2 is, oh, wait a second, 2 moles of H2O. Which means the limiting reagent in this case is actually H2. The maximum amount of product we could make was 1.5 moles of H2O. Let that one sink in. Damn, does it suck to be right. Okay? So, please set up your work, check that process all the way through. This is why it was important to balance equations. This is why we talked about that in Unit 2, so that you had those fundamentals that you could then rely on and use in Unit 3. And so if you were struggling in Unit 2, okay, that's where you should have spent that time to practice it, instead of just being like, well, it won't be a big deal. It is a big deal. It's going to stack, just like I told you back in Unit 2. Okay? So please be aware of that. You need to be thinking about this process and how we build these things out and how we address them. Okay? It is that process that's going to get you through all of these questions. You decide to skip the process, it becomes challenging. Okay? The other big concept that comes out of this chapter is this concept of percent yields, which can be taught to hugely different levels of difficulty. Okay, so the first thing that we're going to go through and do is look at a simple level of difficulty, and then we're going to put this all together into a giant storm of stuff, and you can see how complex it could get pretty quickly. So the whole point of our percent yields is to standardize or normalize our results. Okay, unfortunately, we didn't get to do this lab this semester because all of our labs have now moved online, but let's envision a different scenario. Okay, let's say we all go into our backyards, we dig around in the dirt, you guys stumble across 5 grams of gold. Okay, of gold. So everybody knows, lots of value. You got 5 grams of gold. Well, in my digging around in the backyard, I stumbled across 10 grams of gold. So whose yard should we actually try and dig up to find more gold? Okay? And before you start trying to look up my address where this is, number one, this is a theoretical system. There is not gold in my backyard. I've already looked. Okay? When I searched my backyard, I had to dig through the entire backyard. Okay? When you searched, you only searched a, let's say, 1 foot by 1 foot area. Okay? So if we're looking at it, the gold per potential is much higher in yours, because my backyard is a whole lot larger than 1 foot by 1 foot. Okay? Which means your yard has a greater potential for gold than mine based off of those statistics. Okay? And so what we're trying to do is normalize the result. We have to make sure that where we're finding that is a fair comparison. And this is the point of percent yields. So when we go through to run a reaction, we produce a product. Okay? So A goes to B. Really simple equation. If I just say that I produced 2 grams of B, well, that's not really useful because somebody else could go through and say, well, I produced 4 grams of B. Okay? Does that mean the purple people did better than the blue people? Okay? Well, the blue people at most could have made 2 grams. Okay? So that's their theoretical maximum. The purple people, if they'd fixed their procedure and they actually performed it better, could have obtained 16 grams of product. So when we now go through and look at these as percentages, the blue people have 100% efficiency behind their experiment, or 100% yield. The purple people are sitting at a 25%, assuming I did that math right. Okay? So in that case, the blue people did significantly better than the purple people. This is the whole point of percent yields. There were an awful lot of P's in those statements. Okay? So we need to make sure that we have percent yields so that we can understand or make comparisons between individual experiments. So the process for calculating it is the actual yield, sometimes referred to as an experimental. How much did you actually obtain? And then a theoretical yield. Okay? Well, the theoretical yield ignores the experiment. Okay? So the theoretical yield is effectively what we do in lecture. Okay? We're doing, for lack of a better description, a mathematical masturbation on how much we could possibly produce. Okay? So this is a calculated yield. This is going to require that we run calculations based off of limiting reagents. So our percent yield requires that we go back and we do all of that limiting reactant or reagent calculations that we just talked about. Okay? So next part, what are our units? Well, the experimental, in the situation where we had A goes to B, we're concerned about how much product we produced. So let's say we picked grams of B. Well, if I'm going to do a percent yield, I need to make sure that I'm comparing the amount that I ended with of a particular substance in comparison to how much I could have made of that exact same substance, which means the units of your experimental and your theoretical have to be exactly the same. Same substance and same measurement. Okay? So what does that mean as far as the units on percent yield? Well, the units would now cancel out. Okay? So there are no real units associated with percent yield. So what units should you use for the actual and theoretical yield? Well, a lot of that's going to depend on your preference, because as long as they're the same, it doesn't really matter. Typically, when we're looking at these, the experimental yield is going to come out in grams because we're weighing it. Okay, so it's obtained via a mass. So that means if I'm going to do limiting reagent calculations and I need to eventually get these into the same unit, it sometimes makes sense to end with our limiting reagent calculations in grams of our final product. Okay, but they don't have to be grams. I could take that measurement of mass and I could convert that into moles of B. Well, that just means when I go through and do the limiting reagent calculations that I don't go to grams, I would now go to moles of B. It cuts out a step out of my limiting reactants. It cuts out a step and just moves it up into the experimental. So it doesn't really matter what unit you decide to use for the actual, but once you've defined it, you have to use that same unit for the theoretical. Okay? And I think I can actually show that in the next sequence as well. Okay, so let's go ahead and look at an example. So 2 moles of sodium carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide, and only 0.5 moles of sodium hydrogen carbonate are produced. Then what is the percent yield of sodium hydrogen carbonate? Okay, well, what this is actually asking us to do is all of those calculations that we already ran. Okay, that big list of information at front, okay, all of that is the limiting reagent calculation, okay, or LR. That's the limiting reagent calculation that we ran just a few slides ago. Okay, and if I remember correctly, we said that we could end with 1 mole of sodium hydrogen carbonate. I believe that was our conclusion. Okay, feel free to go back and check me on that, or even go through and look at the units here. Okay, so 1 mole of sodium hydrogen carbonate was our limiting reagent. That was calculated. Because that was calculated, what does that mean? Well, then that means that is our theoretical yield. Okay? If I'm being asked to solve for a percent yield, okay, and this is where things get a bit interesting, the theoretical or percent yield of sodium hydrogen carbonate, I would then need to get an actual yield. An actual yield of what? Well, sodium hydrogen carbonate. And I would then divide that by our theoretical yield of sodium hydrogen carbonate, and then multiply by 100%. Well, as we just discovered, we just identified our theoretical yield because we've already done that question. Okay? If we hadn't already done that, we'd have to resolve all that work. But since you've done a good job actually writing notes as we went through this video, you already have those written down and you don't have to redo it. Okay? What was our actual yield in this case? Well, so the actual yield is our experimental, and it's something that would have to be measured in lab. Okay? Which means in a question, it's going to be given information. And so if we go back and look at our question, we should see that we do have that given information. We produced 0.5 moles of sodium hydrogen carbonate. So now what do I have to do for my calculation? Well, my percent yield will just be 0.5 moles of sodium hydrogen carbonate divided by our 1 mole, where did it go, of sodium hydrogen carbonate, and then we multiply by 100%. Okay, so that would then equal 50%. So we would get a 50% yield. Okay, so what I'm going to ask you do, or ask for you to do, is just to look at this, absorb this, get all those numbers in there. Because what I'm going to do is a slight modification on this and see where it takes us. Okay, so in that see where it takes us. So we're going to erase some of this stuff. Okay, I don't want these numbers. I do want that 50%. We're talking about the yield of sodium hydrogen carbonate, but instead of doing sodium hydrogen carbonate, I'm going to do CO2. So the actual of CO2 and the theoretical of CO2. Okay, so this is an entirely different substance, so this might be weird. Okay, I'm not going to do water or sodium carbonate. So why am I focusing on CO2 and not the other ones? Well, when we ran our limiting reagent calculation, one of the conclusions that we come up with is not only that we produce 1 mole of sodium hydrogen carbonate, so we can add a little step in here, but the other conclusion was that our limiting reagent was CO2. Okay, so the CO2 is what's dictating our sodium hydrogen carbonate. Okay, so what does that mean for us? Well, if we're looking at our actual yield, or sorry, not our actual, our theoretical is now CO2, right? Because that's how I'm now interpreting this, is we're cutting moles of sodium hydrogen carbonate out of this, which means we had 1 mole of CO2. Okay? So what about our actual yield? Well, the actual yield was given as 0.5 moles of sodium hydrogen carbonate. I need to convert that, and of course now I am going to have to erase that to give me a little bit of space. I'm going to have to convert that into CO2. That conversion is going to come from my balanced chemical equation, which is up top. Did I do that right? 0.5 Let's just see. We're just going to push and see what happens. We get 0.5. That's not math. Try that in math. 0.5 divided by 2. Man, I may have to delete this from the video. That would be really irritating. 0.25 moles of CO2. Well, gall darn it. I goofed. Crap. Well, hopefully I can delete this from the video. Hopefully YouTube will let me do that, so I didn't get to do the cool thing that I wanted to do. Dang it. So, next thing that we could do is really explode the difficulty behind this, and we could jump to a question like this. This involves limiting reactant, percent yield, and just a multitude of other things. So, let's go through and process what we've got in here. 50.6 gram sample of magnesium hydroxide. Okay. So one of the steps that we could do, like we've been doing with the other things, would be to change that magnesium hydroxide into a formula, MgOH. Hydroxide has a -1, magnesium has a +2, which means I need 2 hydroxides to make that formula. Is reacted with a certain gram amount of hydrochloric acid. So again, I could switch that around to interpret my hydrochloric acid. It's going to be HCl, hydrogen's a +1, chloride's a -1, so that formula is correct. At the end of the reaction, a chemist recorded a dry mass of 60.0 grams of magnesium chloride. Magnesium's a +2, chloride's a -1. I would need 2 chlorides to balance that. What is the percent yield? Wait, what? That's what I'm supposed to do. That's hardly any information. Okay, so let's kind of walk through this on what we're being asked to do. We need a percent yield. So we know percent yield is actual over theoretical. Okay, the actual is given to us, so that's cool. 60.0 grams of MgCl2. The theoretical has to be calculated. Okay, well, how does it get calculated? It gets calculated through a limiting reactant situation. The limiting reactant situation is going to require doing a substance conversion, which means we need a balanced chemical equation. To get the balanced chemical equation, I would actually need to know my reactants and products. So I would need the formulas for my reactants. I would also need to be able to predict the formulas for my products because I know what kind of chemical reaction this was based off of the information given. Okay, so that doesn't look too bad, except let's really actually explode this down to all of the questions you're being asked to answer. This is ballpark what you're being asked to answer. What is the formula for magnesium hydroxide? What is the formula for hydrochloric acid? What type of reaction occurred? What products were yielded out of this? What is the balanced chemical equation? If all of the magnesium hydroxide became our product, i.e. it's the limiting reagent, how much product could we get? If the hydrochloric acid was the limiting reagent, how much product could we get? Based off of those calculations, which one is the real limiting reagent? Once we know that, then we can use the combination of our actual and theoretical yields to get a percent yield. Holy monkeys, that is a lot of calculations to go through and run. Okay, all of which should be within your wheelhouse, and you should be able to do this in a matter of minutes. Okay, so what I'm going to go through and do is advance the slide once because it cleans it all up. I believe, yep, it gets rid of all of that text. And then I think you should spend some time to try and go through and solve that. Meanwhile, I will be doing the same thing, but in a paused situation. And you can then go through and look at that answer to see if that work matches the work that you went through and did. And so with that, I'm going to say, please pause the video. Yep, that means pause. Click the picture. Hit the space bar, throw the computer out. Don't throw the computer out the window because you probably need it. Okay, but pause, start actually doing some work on this and see what you can come up with. I hope you're ready for this, but here it all comes. Boom. There's everything you needed to go through and solve this. It's a lot. All of that work is there. Okay? There's a couple things, I think only one thing that I really wanted to point out within this is that when we get to that final answer, we end with a percent yield that is over 100%. And for those people being like, but you can't have 100%, over 100% yield, this is your question. Because now what happens is you're like, well, I must have screwed up. And I must mean that instead of 58.8 being the magnesium chloride, it must be the 82.6. And guess what? That answer choice also shows up as a potential answer. Okay, you can have a greater than 100% yield. It means that you experimentally screwed something up. Okay, so the statement that you can't make more than what you started with is that in a real world sense, you shouldn't be able to do that. What's happening here is that experimentally something was goofed. You are making the assumption that the question removes experimental failures. Don't be making assumptions because I already do that enough, and I already am enough of a donkey. On my own, I don't need you making me one as well. Okay? So don't start jumping to assumptions. If your calculations tell you that you have something greater than what you would expect, what you can do is check your work. But if you can't find a mistake in your work, don't start second guessing it. Run with what your work tells you it is. Okay. So that's a super exciting question. I don't really want to end on something so horribly drastic, so I'm going to go through and we're going to alter this question a little bit. Okay, so I'm going to delete everything, so hopefully it's up there for long enough. Hopefully you can see all the color coding, where things were coming from, all that fun jazz. And oh, this hurts so much, but here we go. We're going to delete it all, and we're going to switch up the question. So I'm not going to delete it all because I want some of that. So I'm going to pause real quickly. Okay, so I made some big changes here. We still needed the chemical equation. So what we're changing this up to now is just a limiting reagent or reactant question. Reagents versus reactants are the same thing. And I want to ask the question, what is the limiting reagent? Okay, so this is a little bit different than how we looked at our limiting reagents in the past, because in this case, all I'm asking is what is the limiting reagent? Okay, so based off of how we talked about it before, we need to decide, pick a product to solve for. So grams of magnesium chloride. And we could go through and look at all of that work that we had written up there that I just now realized I deleted. Okay, but we don't have to go through all of that because we aren't being asked how much product was being made. We just want to know which of those things is the limiting reagent. To make that comparison, we just have to be in the same unit. Okay, what do I mean by that? Okay, well, I could go through and freeze the hydrochloric acid. Okay, so instead of doing anything with that number, I'm just going to say I have 45 grams of hydrochloric acid. And what I'm instead going to do is I'm going to take my grams of magnesium hydroxide and I'm going to turn that into grams of hydrochloric acid. So the question I'm now asking myself is, if I react 50.6 grams of magnesium chloride, how much acid do I need to react it with? Okay, so again, we can set up our conversion, our HCl, our magnesium, hydroxide. Okay, this coming from the chemical equation means we need moles for each of those. 2 moles of HCl, 1 mole of magnesium chloride. So that conversion from our balanced chemical equation. So not really different than what we looked at before, at least not yet. Okay, I need to get rid of the moles of magnesium hydroxide. So I'm going to place that up here, moles magnesium hydroxide, grams of magnesium hydroxide, and of course, I deleted all that information and I don't know its molar mass, so we'll do a weird pause, but that information is going to come from our periodic table. So when we had that, our moles of magnesium hydroxide, that's color code, moles of magnesium hydroxide cancel. Okay, I need to get rid of my grams of magnesium hydroxide. Okay, and organize this oddly, I need to get my moles, of HCl to get into grams of HCl, right? That one I actually have quickly calculated in my head. 36.45 grams of HCl is 1 mole of HCl. So that's useful because that gets rid of moles of HCl and actually brings in the unit that I want, the grams of HCl. And that also came from the periodic table. And then I could go through and multiply by the grams of magnesium hydroxide I started with. Okay, in this case, which we said was the 50.6, right? Okay, and so now we're going to get that weird potential pause. So when we come back, I was able to get the periodic table, or use the periodic table to determine the molar mass for our magnesium hydroxide, and then I ran the calculation, and I would get that if I was to react all of the magnesium hydroxide that I was given, I need 63.3 grams of HCl. Well, how much HCl was I given? I was only given 45, which means I have less HCl than needed to react all of the magnesium hydroxide, which means the HCl is my limiting reactant. And for those of you saying this is still a lot of calculations, it is, okay? But if we ran our limiting reagent calculation the way that we've been talking about it, in terms of getting it to the product, we would have to do this calculation twice. Once for the magnesium hydroxide, once for the HCl. So if the question changes to be what's the limiting reagent, you only have to do one of those conversions. So if you're intelligent or thoughtful, I think is probably the more appropriate term, thoughtful about the calculations you're running, you can simplify the amount of work you have to do. Okay, so that's the last big thing I wanted to get in on limiting reagents, because you don't have to brute force all of those calculations. You can be a little bit more subtle behind it and get to those answers better. And so with that, I'm going to go ahead and end this video, and hopefully my reference here to the weird section in the middle of this video you don't know about because I was able to delete it.